100,000 people. Fast forward several centuries, and we reach the dawn of modern independent hydropower. It started with a fortunate accident in a Sierra Nevada gold mine involving a carpenter named Lester Pelton. In the 1870s, mining operations were burning through entire forests just to power their steam engines. The existing water wheels of that era featured flat blades and achieved a disappointing 40% efficiency at best. Pelton happened to be watching one of these wheels when the pin securing it to the drive shaft came loose. Suddenly, the water jet that normally hit the center of the buckets struck the edge instead. Surprisingly, rather than slowing the wheel, this change caused it to spin faster than ever. In that instant, Pelton made one of the most significant observations in mechanical engineering history. It wasn't simply about hitting the blades with water. The real secret was reversing the water's direction as completely as possible to capture every bit of its momentum. He developed a specialized bucket design featuring a central ridge or splitter. This divider split the incoming jet and turned it nearly 180 degrees. By 1880, his improved wheel achieved over 90% efficiency. This breakthrough allowed remote homes and small mines to generate meaningful power from high mountain streams that were previously considered useless for energy production. Even slightly earlier, in 1878, industrialist Sir William Armstrong had installed a single turbine to light his home in Northumberland, England, making it the first private residence in history powered entirely by falling water. The term Pico hydro emerged soon after to describe hydroelectric generation systems producing under 5 kilowatts. For a short but significant period between 1880 and 1930, decentralized hydropower became woven into the everyday life of the Western world. Thousands of isolated homesteads and small communities operated their own lighting plants. By the early 1900s, the steady hum of a Pelton wheel symbolized true energy independence. However, that era of self-reliance was gradually dismantled. Before we explore how to construct your own Pico hydro system, it's essential to understand precisely how these setups operate. Pico hydro installations vary widely in design, but unlike massive hydroelectric dams, they typically avoid impounding rivers. Instead, they employ a run-of-river method, diverting only a small fraction of the stream flow without creating reservoirs. The process starts with a carefully designed intake. The most sophisticated versions use Coanda effect screens, specialized wedge wire grate that leverage the natural surface tension of water. Water adheres to the curved surface and falls through into the collection channel, while debris, leaves, sticks, and silt wash harmlessly over the top and back into the stream. From the intake, water flows into a 4-bay tank. Here, the velocity decreases, allowing heavier particles like sand and silt to settle at the bottom before the cleaner water proceeds into the pipeline. Next comes the penstock, a pressurized pipe that carries the water downhill. This section is where the fundamental physics of head, vertical drop and flow, volume of water, become critical. As water descends the pipe, the weight of the column above it builds pressure at the lower end. For every 10 feet of vertical drop, you gain approximately 4.3 pounds per square inch of pressure. At the base of the slope, inside a compact powerhouse, the pipe narrows into a precision nozzle. This nozzle transforms the built-up pressure into a high-speed jet directed straight at the curved buckets of a Pelton wheel or similar turbine runner. The spinning shaft connects directly to a permanent magnet alternator. Unlike many generators, this type produces electricity immediately as the shaft rotates, without requiring any external excitation source. It generates raw alternating current from the motion. Here's what truly sets Pico hydro apart from idle for about 3/4 of its installed life. Pico hydro systems, by contrast, routinely achieve capacity factors of 95% or higher. A 1 kilowatt hydro turbine delivers 1 kilowatt of power every single hour of every day. Over 24 hours, that's a full 24 kilowatt hours of energy. To match that same daily output with solar, you'd need at least a 6 kilowatt array to compensate for nighttime hours and suboptimal sun angles. This disparity creates enormous differences in battery storage requirements. Solar-dependent users must invest in massive banks of lead-acid or lithium batteries to cover the long gaps between sunset and sunrise. Hydro users, however, often need no batteries whatsoever, or perhaps only a minimal buffer bank for brief stability. When a suitable site with reliable year-round flow is available, the stream itself effectively becomes your battery. The gravitational potential energy stored in elevated water proves far more of stringing copper wires across vast distances, the government effectively eliminated the financial motivation for individuals to maintain personal power system. Over 2 generations, the practical knowledge required to service Pelton wheels, including plumbing expertise, bearing maintenance and nozzle adjustments, faded from common culture. Society traded freely available local energy sources for the convenience of a monthly utility bill and dependence on large-scale centralized generation controlled by major corporations and utilities. Today, regulatory hurdles can make implementing these systems challenging. In the United States, the Federal Energy Regulatory Commission, FERC, asserts authority over any hydropower project impacting navigable waterways. Although exemptions now exist for very small installations, a run-of-river project on a natural stream may still require an extensive permitting process, lasting up to a year and costing thousands in environmental assessments and studies. Additional complications arise from differing state water laws. In eastern states, the riparian doctrine generally applies. of the stream during normal conditions. For basic economic viability, you'll generally need at least 50 feet of vertical drop combined with a minimum of 10 gallons per minute of consistent flow. Below these thresholds, the project often fails to justify the effort and materials required. Maintenance represents another important consideration. Unlike solar panels that require almost no attention, a hydro installation is an active, living system. Intake screens can clog after heavy storms, bearings gradually wear down, and pipes may freeze during severe winters in colder climates. This is not a completely hands-off technology. Regular inspection and seasonal maintenance are necessary to maintain peak efficiency and prevent unexpected failure. However, for property owners who possess suitable land, reliable water sources, and the commitment to ongoing care, the barriers to entry have decreased substantially over the past 2 decades thanks to technological improvements and better information sharing. Ready-made commercial solutions provide the simplest route for many people. Companies such as PowerSprout and Scott Hydro now manufacture complete integrated turbine units. These systems are designed to mount securely onto a concrete pad and connect directly into contemporary inverter setup with minimal additional configuration. For budget-conscious builders, several DIY approaches offer excellent alternatives. One particularly clever strategy involves the pumper's turbine method. Standard centrifugal water pumps, originally designed to consume electricity to move water, can actually generate electricity when water is forced through them in reverse. Because these pumps are mass-produced for agricultural use and readily available at local hardware stores, they provide a durable, industrial-quality foundation for a fraction of the price of purpose-built turbines. Currently, one of the most accessible and affordable entry points for independent builders comes from the outstanding open-source contributions of Daniel Cornell. His innovative high-performance designs enable anyone to construct a fully functional turbine for under $50 using readily available common materials and basic hand tool. I will include a link to his open source resources in the video description below. Connell's work forms part of a growing global movement focused on open source appropriate technology. These efforts aim to democratize the tools of energy independence, making detailed blueprints available to anyone possessing basic skills and determination. By utilizing these community-tested and validated designs, you can completely bypass expensive specialized markets. Instead, you'll create a custom system capable of converting an ordinary backyard stream into a dependable, continuous source of electrical power for your home and family. No matter which approach you ultimately choose, commercial unit, pumpers turbine conversion, or full open source build, the single most critical step occurs long before you pick up any tools or place any orders. That step is carefully measuring your stream's flow during the driest season. Do not base your calculations on spring flooding or average autumn conditions. Design your entire system around the minimum flow available in August after several weeks of drought and low rainfall. A modest installation producing a steady 500 watts continuously throughout the dry summer months will prove far more valuable than a larger system generating 5,000 watts for only a couple of months each year before becoming useless during dry periods. The Pico hydrogenerator beautifully bridges the brilliant mechanical engineering achievements of the 19th century with the sophisticated power electronics of the 21st century. It demonstrates convincingly that a simple flowing stream can deliver greater long-term energy security than decades of incremental improvements in battery storage technology. If you found this information valuable and inspiring, please consider subscribing to the channel. We regularly share practical tips, innovative techniques, and real-world solutions designed to help you achieve a more independent, self-sufficient lifestyle.